So this is unlock circuits 18EC42. We are discussing the module 1. We are in lecture 3, small signal operation and models. So in the last class, we took up the biasing of the BJT and some of the examples concerned with the biasing of the BJT. Now we are discussing the same thing, BJT itself, that is the bipolar junction transistor, but we will consider how its operation is whenever we talk about, consider the small signal. That is, small signal just means, the input is very small, and also what are the models for this corresponding to it. Okay, what are the models corresponding to the small signal is what we will try to see today. So when we take that, then at the input side, the most important things which we should consider is that we have the DC, the AC signal, which we generally call it as input, and together the DC plus the AC will be known as the instantaneous value. So this is the instantaneous value, this is the DC value, this is the AC value, which is the input signal. Okay, whenever we use small v and capital BE, right? Suffix is capital, but otherwise the symbol is small, then it is the instantaneous value, which is the sum of both the DC and the AC. When both the variable as well as its suffix are capital letters, then that is the DC value. And when both the suffix as well as the uh, value itself V is small, both are small here, then that is the input signal or AC signal. So this is the signal which has to be amplified, right? This is the signal which has to be amplified. And this DC, what is the purpose of the DC? The purpose of the DC is to bias the transistor properly. The purpose of the DC is to bias the transistor properly so that, we fix the quiescent operating point. Quiescent term is used to consider that we don't have any input signal. Whenever no input signal is there, then that value becomes the quiescent value. Okay, quiescent value. So quiescent operating point should be in the middle of the load line, and hence we need to have this, DC value. So DC plus the input AC signal, which is to be amplified, corresponds to the instantaneous value over here. So that's why here, we have written the DC plus the AC. So remember that this DC VBE is only because of the biasing. And that biasing indirectly will be just because of, if you consider the voltage divider bias, then it is because of the two biasing resistors R1, R2, as well as the VCC, which we have connected here, right? In the last class we have connected here, or might be the collector to base bias. Due to the collector to base bias, whatever is the voltage at the base, that also can be considered for VB. So depending upon whichever, it doesn't matter which what we call biasing schemes we use. Okay, different biasing schemes give different kind of stability. Okay, one of them is used. Whichever is used will have the value of VB, which is equal to VBB. So that will be the biasing DC value. Okay, biasing DC value, because of which we will have some DC at the output also. Okay. So the DC bias condition will be the case when we set the small VBE over here equal to 0. When this VB is 0, then we'll have this circuit over here, right? So, and this is nothing but the biasing model, because what we are doing is this is just replaced by either the potential divider network over here or the collector to base bias resistor over here. That's all. Okay. Either way, VBE is equal to the VBB in the biasing circuit which you are considering in the last class. Okay. So at that time, when we have the you can see that this is the instantaneous value when both the AC and DC are there. This is the instantaneous value because you have both AC and DC there. And this is also the instantaneous value. All these are instantaneous. Because input is instantaneous, this, as well as this is instantaneous. Okay, this together will become the instantaneous. This current, base current is instantaneous. Emitter current is instantaneous. The collector current is instantaneous. The VCE value is also instantaneous here. So when we make the small VBE, which is the input signal which is to be amplified, or the AC signal equal to 0, then we'll have just the DC value here. Okay, we'll have the DC value over here, right? So and if we what you call have the DC value here, all these will be just DC. IC, IB, IE will be all DC. Okay, so you might have chosen some part to be studied and some to be left, but please remember that whatever we do in this will be dependent. A lot of subject syllabus will be dependent upon this circuit. Okay, so all these are DC values because we have applied here the DC value. IB, IC, IE, VCE, and all that. Fine. So under that condition, the IC, the collector current, will be equal to the IS. IS is the saturation current, ideally reverse saturation current, multiplied by e to the power of VB by VT. This is the standard, model. This is the standard diode equivalent circuit where IC is equal to IS. IS is the reverse saturation current. Some people call it as ICBO also in place of IS, but here he has simplified the symbol and put IS to refer to the saturation current, right? Reverse saturation current. E to the power of, here it will be the capital VB because this is capital IC by VT. Similarly, the value of IB is nothing but the base current is equal to collector current by beta, or collector current is equal to base current into beta, beta into the base current. Again, this is the standard formula which is there over here. Then we'll have here IE. IE will be equal to IC by alpha, or IC will be equal to alpha IE. These are all standard values. Then here, if you see this value over here, this is VCE. This is VCE, and that VCE is equal to this VCC minus the drop across this. If you take the loop equation at the output, then VCC is equal to ICRC plus VCE. So VCE will be equal to VCC minus ICRC, and that's what is being mentioned over here. So, whenever, why do we do biasing? Biasing we do so that we fix the quiescent operating point in the middle of the load line, and that will correspond to taking the transistor into the linear region, and linear region is basically the active, region or active mode of operation. And for that, we'll have the VC value, greater than VB minus the, 0.4. Okay, VB minus the 0.4. So the 0.4 might be the minimum voltage which is needed to drive the transistor to on. So ideally it might not be 0.4, it might be 0.6. Okay, so the value of VB should be greater than ideally 0.6. He has taken 0.4. Do not bother much about this value. Okay, so this is the DC model, whereas this will be the instantaneous model, where we have joined both the components of AC and DC together. Okay, so this is all these values are DC values over here. Okay, now the collector current, and the transconductance equations to be derived over here. So the instantaneous value VBE is equal to the DC value plus the input signal to be amplified. That is what we have written earlier also, this itself. Okay, this equation itself we are repeating over there. And this value of VBE, we have, the value of VBE and, this VBE to be substituted some way into some of the equation. And IC is, this is instantaneous value of the current. Instantaneous value of the current IC will be again equal to the DC value of IC plus the AC value of IC. And that will be equal to IS into e to the power of, this is, the VB being used over here is the instantaneous value of VT. And this VB is substituted from over here, and we'll get this. So you can separate it out, IS e to the power of VB by VT, e to the power of small, VBE by VT. So this is the DC component, and this is the AC component over here. And we know very well that this, merged with this will be nothing but the, capital IC, which we have considered in the equation over here, right? This is the equation which we have considered over here. And, so this quantity is IC, and this is what is left off. And therefore, the IC value will be equal to, the instantaneous value of IC is equal to the DC value of the IC multiplied by e to the power of the input VBE divided by the VT, where VT is the old thermal equivalent. So this is, in standard value of this is 25 millivolts. VT is 25 millivolts. Okay, that is the standard value. So you can write the, whenever we have e to the power of x, then that can be written, as 1 plus x square by 2 factorial plus x cube by 3 factorial plus x to the power of 4 by 4 factorial, and so on. We can keep on writing like that. Whenever e to the power of x we have, that we can write it as 1 plus x square by 2 factorial plus x cube by 3 factorial plus x to the power of 4 by 4 factorial. And whenever, x is very small, that is, the quantity to the power is very small, then all higher order terms can be neglected. We'll take only the first two terms, that is 1 plus x is the approximation. Okay, and that 1 plus x approximation is written over here. Okay, only under the condition that the value here is very, very small, lesser than 1. Generally we consider this to be much lesser than 1. So when this is much lesser than 1, because of the reason that if we consider e to the power of 0, then it will be 1. If it is some positive value e to the power of some positive value, it will be more than 1. So it should be 1 plus something. So in that sense, if we take, if VBE by VT is less than 1, then VB is less than VT. So under that condition, we can consider this as 1 plus x IC into 1 plus x. Okay, so you can separate this out, IC plus IC into VB, what you call E divided by VT. Okay, so I said already that this is the instantaneous current, which will be equal to the DC value of the current plus the AC value of the current. So because IC is the AC value of the current, then this multiplied by IC will become the DC value of the, that value will be the AC value of the current. IC multiplied by this will be the AC value of the current, because we have here IC into 1 as the DC value. So DC plus AC will give us the instantaneous value of the current. So therefore, the DC value of the current over here will be, that's what we have written here. This we have separated out over here, right? We have separated it out, and we have written the instantaneous value as the DC value plus the AC value. That means, you can see that this AC value will be equal to this value, and that's what we have written over here. And this IC by VT is, you can just take it on the two terms. That means the GM is generally defined as the VBE by IC. VBE by IC is defined as GM, and hence, if you write VB by IC, then that will be equal to IC by VBE. If I take this VBE over here, then I'll get the value of GM. GM will be equal to IC by VBE, and that will be equal to IC by VT, and that's what we have written over here. So either you can say IC is equal to GM VBE, or GM will be equal to IC by VT. Okay, GM will be equal to IC by VT. Now, why do we call it as GM at all? The term GM here is referred to by the term transconductance. And what is this? Conductance just means current by voltage. Okay, current by voltage is conductance, and trans is basically referring to transfer. Transfer just means output by input. So conductance is basically the value output current by input, current by the voltage. Current by voltage is conductance. The trans term is output by input. So if you join these two terminology, then you'll get output current by input voltage. Output current by input voltage is what is known as transconductance. And output current we know very well is IC, and input voltage we know very well is VBE, right? VBE is the input voltage, right? Input signal, AC signal, and IC is the output current. That is why GM is transconductance. Okay, so this GM is directly proportional to the collector bias current IC, and it is inversely proportional to the value of VT, that is the volt thermal equivalent. So this value is 25 millivolts, 25 millivolts standard. Okay, so sometimes when we that or at room temperature, this value is 25 millivolts. So sometimes people might write this as GM is equal to 40 IC. 25 millivolts if you put at the denominator, that will just turn out to be 40 into IC. Okay, so for a constant predictable GM, we have a constant predictable IC is required. You want a constant value of GM, then you need a constant IC, because VT is just constant. Okay, so BJT have relatively high transconductance of the order of 40 milliamperes per volt, IC equal to 1 milliampere. So when IC is equal to 1 milliampere, 1 milliampere by 25 milliampere will give us the value, which is 1 milliampere by the 25 millivolts will just give us the value which is equal to 40 milliamperes per volt. Okay, 40 milliamperes per volt. Okay, so that is the value we can find for GM. Now let us consider the graphical interpretation of this GM. So for that we are trying to write here the characteristic, which is the transfer characteristic. What is transfer characteristic? Input voltage, input instantaneous voltage, input instantaneous voltage. Please remember that instantaneous voltage is what we are considering here, and output instantaneous current curve. Okay, the term which corresponds to the transfer characteristic over here is IC versus VBE. VBE is the instantaneous voltage, input voltage. IC is the instantaneous output current. Okay, both are instantaneous, right? In the graph, we are considering both as the instantaneous values. Okay, so when we talk about this over here, then there is only a very small region over here. Rather, this is the quiescent operating point, and quiescent operating point straight away will correspond to the DC value of the input voltage, that is capital VBE, and also the DC value of the current, which is IC, as the point over here on this side. And on this side we take a small linear region Okay, a small linear region under through which it should operate. Okay, it should operate. So above and below this DC value is what we will have the signal. The signal is the input signal. So above means this side, below means this side. This is the DC value of the VBE. This is the DC value of the EIC, right? And if you say this is the DC value of VBE, above and below will have either the triangular wave or the sine wave, whatever we want, which is the AC signal. Okay. Okay. If you consider single frequency, then you will consider here a sine wave. But if you want that, multiple frequencies, harmonics also to be there, you can consider either a triangular waveform or a square wave. Generally, we'll consider triangular waveform because that will give proper reproduction of the signal over here, right? Proper reproduction of the signal over here, right? So, this AC signal, input AC signal over here is amplified, or rather, if you take it out over here, because of the AC input signal, small v, VE, we'll have the, what you call, AC, so to say, the value of current, output current, IC, output current IC. So this variation is IC. This variation is IC. This variation is small VB. But to this, if you add the DC value, which is this, then this becomes instantaneous value together. If you add to this the value IC, then that becomes the instantaneous value. So for instantaneous value input, we'll have instantaneous value output. Whereas if we try to remove the DC component, then we need to consider that for this value of input, we have this value of the output. Okay. So for that, you can write this IC by VBE, or you can consider a small change in the instantaneous value. GM is equal to del IC by del VBE when IC is equal to capital IC. This is the instantaneous value is equal to capital IC. Okay, that is at the the slope at the point where we have the DC value. This is what it means when we assign this. The slope at the point at which we have the DC value. What is the slope of this curve? Is what which we are taking, that is dou IC by dou VBE. Okay, at the time IC is equal to IC. So this is the small signal representation of the overall, so to say, the transconductance. So our operation is basically restricted to the small region over here. Operation is restricted to almost linear segment of the ICVB exponential curve. So this is an exponential curve, but we operate only during this, and that will be the region which will correspond to the active region. That will be the one which will correspond to the active region. Okay, so below this it might be in the cutoff region. Above that it might be in the saturation region, but this is the region which will just correspond to the active region. Okay, so for small signal we have already written VB should be very much less than VT. That means VT is 25 millivolts, so VB should be less than the 25 millivolts. Then only the small signal, so to say, operation will be effective. Otherwise, we cannot say that. Okay. So under small signal conditions, this is equal to the GM VBE. This is equal to GM into this, or you can, that is what we have written over here, and that is what we have derived in the previous slide. Okay, that's what we have derived in the previous slide here. IC by is equal to GMVB. Same thing we have used over here, and that is small signal. And large signal will be the both the AC plus the DC. That will just correspond to the instantaneous value. Okay, rather than calling it as large signal, it is always better to call it as instantaneous value, which is the sum of the DC bias value IC and the small signal current, which is small IC. Okay, so linear operation of the transistor under the small signal conditions, generally we'll consider that under small signal conditions, the operation is linear. A small signal VBE with a triangular waveform is what we have superimposed on the DC value, right, VB, and corresponding to that, we'll have the small signal value of the IC, which is again superimposed on the DC value, which will correspond to capital IC. Okay, it gives rise to a collector current IC, also a triangular waveform superimposed on the DC current IC. So for what it means is corresponding to this value, we'll have this IC. And if you add both together, VBE with this, then you get this with this. Okay, where the relationship between IC and VBE is this. IC is equal to GM VBE. So thus we give a representation of the graphical representation of the GM and the transfer characteristic. From the transfer characteristic, we can get the transconductance. Okay. So then we come to the base current and the input resistance of at the base, right? So I think I'll rather stop at the recording now.